Kinetic theories. The rate of a reaction depends upon the behavior of the particles that are in the reaction system. There are various influencing factors on the kinetic behavior of a system. The nature of the reactants, the way that they're comprised, the way that the reactants are split up, all of this will affect the rate the reaction undergoes. The concentration of reactants will affect the kinetics, as we've seen with the rate law and the time-integrated rate law. Temperature will affect kinetics because increases in temperature will increase the speed with which particles move. This causes the particles to be able to react in a faster time scale. And the presence of a catalyst will also affect kinetics because catalysts are designed to cause the system to react faster. There are two basic theories on the behavior of particles in kinetics. The first is collision theory, which looks at how particles combine in a system in order to actually undergo chemical reactions and relates that to the speed of the reaction. The second is transition state theory, which looks at the energetics of the reaction and uses this as a governing principle for the rate the reaction undergoes. Now, the collision theory of reaction rates states that particles must quote-unquote collide in order to react. The higher the concentration of particles, the more collisions are going to occur over the course of a second, therefore the rate will be faster. If we have a higher temperature situation, the particles will be moving faster, which also means that they'll be coming into more collisions per second. Now, the collisions which occur must be what we call effective collisions, not just any random collisions. And to be an effective collision, a collision has to have two properties. It has to achieve a certain minimum energy in order to accomplish the bond changes that have to be accomplished within the reaction. Any sort of bond breaking process has to input energy into the substance in order to break bonds. If we are going to do this bond process, then the collision has to occur with a high enough energy to overcome the energy needed to be input into this bond breaking process. Now, when we make bonds, we will have a release of energy, which may have an overall net decrease from the starting material to the reactant, but in order to get through the reaction process, we have to increase enough energy to break the bonds first before we can make new bonds and lower the overall energy. In addition to having the proper minimum energy, a collision must also occur with proper orientation. If the atoms which need to form bonds are not oriented near each other, they're not going to be able to overlap their valence configuration properly in order to get a bond. Now, when we talk about colliding, we're not really referring to a physical collision between two things. We're actually referring to a certain proximity that the atoms have to reach, or the distance the atoms have to come in order to make bonds by overlapping their valence shells. The reaction distance depends upon the nature of the particles themselves. For something in the gas phase, for instance, if we have an ion or a permanent dipole, we'll find that the distance is much longer than something like a dispersion force. Also, if we were going to compare or to react something with ionic interactions or permanent dipoles with something with an induced dipole, what we would call a dispersion force, that also will tend to be a longer interaction than a simple dispersion force as well. So the smallest interactions we get come from dispersion forces by themselves. The longest come from interactions with ions, and things in between wind up as moderate proximity. The reason for this, remember, is that the force of the attraction between two atoms is equal to the magnitude of the charges divided by the distance to a factor of x. Now, for x depends upon the nature of the charges we're dealing with. For an ionic substance, it's 2. For a permanent dipole, it's 4. And for an induced dipole, it's 7. So as we move from ionic substances to induced dipoles, we wind up getting a substantially higher exponent, which means that as the distance factor increases, force decreases exponentially faster as we move from ions to dispersion forces. If we look, for example, at the reaction of charged methane, CH4+, with CH4, this will produce CH5+ and CH3. And the distance this can be accomplished over is much greater than the distance between the reaction of two CH3 molecules to make C2H6. Reaction rates are higher with temperature because the energy distribution is higher on average than with a lower temperature. If we look at the average kinetic energy of two temperature distributions, something with a higher average temperature have a higher average speed means that a higher percentage of particles are going to be at this higher energy level. The higher the number of particles at the proper energy level, the more effective collisions we'll be able to get out of the system. So the more molecules are able to react with proper energy. In addition, they'll be moving faster, which means that there are going to be more actual collisions per second, regardless of whether those collisions are effective or not effective. Remember that effective collisions need both a proper energy distribution and a proper orientation. But the higher the temperature, the higher the overall energy is going to be, which means the more likely the particle will be in the proper energy configuration. And even if orientation is not correct, there'll be more frequent chances for particles to come together and have that proper orientation if there's a higher temperature distribution. If I look at the way that an effective collision occurs, if we take this reaction here, presuming that we need to take the one molecule, which is two reds, and the one molecule with a red and a blue, and react them such that one of the reds is bonded to the molecule with the red and blue to make two reds and one blue, releasing the remaining atom to be free on its own. If these come together in such a way as the red and the blue are adjacent to each other, they can form a bond to make the proper molecule, as you see here. But if they come together in such a way as two reds are adjacent to each other, they're not going to be able to get the proper overlap, and they're not going to be able to react. And so the molecules will just bounce off each other and have to try again at a later point. Transition state theory, or TST, is the second kinetic theory that we're going to deal with. Reactions occur when bonds break or form in substances. The potential energy combination for one substance differs from another substance. A carbon dioxide molecule, for instance, has a different overall potential energy than a water molecule does. The internal energy that exists in a substance is going to be different from the internal energy that exists in another substance then because of this. So as I change from one substance into another substance, the internal energy is going to change as well, and there'll be a net difference in internal energy between those two substances. If we take a generic reaction A plus B2 going to AB plus B, there are two possibilities depending upon whether or not the reaction is exothermic or endothermic. If it is exothermic, there'll be a net decrease in the internal energy of the system, so that the products will be lower in energy than the reactants. If the system is endothermic, there will be a net increase in the internal energy of the system, so the products will be higher in energy than the reactants. Usually, we must break bonds in a reaction for it to occur. And as we were saying with collision theory, you need to input a certain amount of energy in order to break these bonds. If we don't have sufficient energy to break the bond for the reaction, then we're not going to be able to have it occur. The energy that we're going to input into the system has to be greater than the overall stabilization that the atoms get from their bonding configuration in order to be able to achieve a bond breaking. And then once they are free, then they can recombine in a way that will produce a net decrease in energy when they come back together as bonds. And the overall nature of that will depend upon whether the reaction is exothermic or endothermic. Now, transition state theory says that a reaction occurs by a short-lived intermediate. These short-lived intermediates are high energy, and they serve as an intermediate configuration between products and reactants. So these little intermediates are basically a transition between product and reactant in terms of the physical nature of these systems. They represent unformed or unforming bonds in transition state theory using dashed lines. So if you look at a reaction with the A plus BB as a reactant going to AB plus B, in order for this reaction to occur, the bond between the two B's has to break, and a bond has to form between the A and one of the B's. As we're going from reactant to product, a bond begins to form between A and B, and a bond is breaking between B and B. This is the transition state, or TS, where we're having a bond forming, the unformed bond on the left, and then a bond breaking, the unforming bond on the right. The kinetic energy that is necessary to get from reactant to transition state is referred to as the activation energy, or E sub A. We can think of this as moving up a hill. If I take a boulder and I'm pushing a boulder up a hill, I have to input energy into that boulder to get it to move to the top of the hill. When it reaches the top of the hill, it is analogous to being in a transition state configuration. If the energy in A and B2 is less than the activation energy that is necessary for the reaction, then I won't get a reaction. So looking at two processes, exothermic and endothermic, on the left and right, respectively. For an exothermic process, I start with my reactants, and I move uphill to the point where I reach my transition state. The energy needed to get there is EA, the red line. The reaction energy, delta E, is the distance between that red line and the green line at the bottom, which represents the energy of the product. Now, I can have a reverse reaction in which the product reforms reactant, and it has an activation energy as well, which is going to be EA reverse, going backwards up the hill. So from the transition state at the top of the hill, I can either go to the right and go down to product, or I can go to the left and go back to reactant. Going from the left to the right, I have to go over a certain amount of distance to reach the top. From the right to the left, I have to go through a certain amount of distance to reach the top. The same thing is true for an endothermic reaction, the only difference being that instead of a net decrease in energy from reactant to product, we have a net increase in energy. So for an exothermic reaction, the reverse reaction has a higher activation energy. The EA reverse is larger than the EA. For an endothermic reaction, the reverse reaction has a lower activation energy, where the EA reverse is less than the EA. The transition state is the high point. As we move away from the transition state, energy will decrease. If we have a net release in energy, we'll be giving off more than we absorb to reach the transition state, and it is exothermic. If we have a net absorption of energy, we're giving off less than was absorbed to reach the transition state, and it's endothermic. The net release or absorption of energy is referred to as this delta E of reaction. The reverse reaction requires the product's energy to be greater than or equal to the reverse barrier, the EA reverse, to reach transition state from the right-hand side. So an exothermic reaction, EA reverse is greater than EA. For an endothermic reaction, EA reverse is less than EA. The delta E of the reaction then overall is the difference between the EA of the forward process and the EA of the reverse process. Higher temperature will skew the distribution towards a higher energy, so a higher percentage of particles will have energy greater than the activation energy. A catalyst will also alter the pathway, which lowers the activation energy barrier. Looking at an example of an actual reaction, the combination of iodide with CH3Cl produces CH3I and chloride ion. The mechanism for this requires that a bond form between the carbon and the iodine. It comes from the back side of the CH3Cl, forming the Ci bond as the CCl bond breaks. So if we see here, from the left-hand side, the iodine is forming a bond to the carbon, and on the right-hand side, the chlorine is breaking a bond with the carbon. The transition state puts the hydrogens in a planar configuration. The chlorine and the iodine are both axial to each other. The overall configuration resembles a trigonal bipyramidal electronic geometry. If we look at a transition state diagram for this, we have the product and the reactant, where the reactant on the left-hand side has the iodine coming in from the left to the back of the carbon that looks kind of like a tripod. Then we have an activation energy necessary to reach the transition state, where we've got this planar configuration, and then moving downhill from there, we have a reversed process where the hydrogens are now on the right instead of pointing to the left, and the iodine is bonded to the carbon. The chlorine is leaving then. The difference between the activation energies is actually in favor of the reverse reaction, so this is an endothermic process, an overall increase in energy.